Hi folks, in this video we're going to have a look at how we can calculate phase difference. So in this question we have a wave which has an amplitude of 4 centimeters and a frequency of 5 Hz, travels along a stretched wire at a speed of 10 meters per second. So the first part of the question we're being asked to calculate the period and then to sketch a graph of displacement against time to represent that wave showing 2 complete cycles. So if we look first of all then at calculating the period of this wave, we know that we have this equation that relates the time period to the frequency, where t is equal to 1 over f, and we're given frequency in the question. So the time period is 1 over 5 Hz. If we pop that into a calculator, we get an answer of 0.2 seconds. So the time for one complete wave is equal to 0.2 seconds. Now we're being asked to sketch 2 full complete cycles on a graph of displacement against time. So let's first sketch out the axes and sketch 2 full wave cycles. So at the moment, I haven't drawn the actual wave in, but what I have done is identify some of the key points on the graph that I want to hit whenever I'm sketching out this graph. So along the x-axis, I have a series of lines, and each of those lines is representing a quarter of a wavelength. I've also put a little dot at the peaks and the troughs of the wave, and you'll notice that they're at the same height because we know the amplitude here is constant. So I'm taking care to make sure that they're always at the same height above and below. In addition to identifying the crests and the troughs, I've also identified the points where the wave is going to cross over the axes. So for one full wavelength, I will have identified 4 points. So once I've identified those key points that I want to hit as the wave travels through, I can then smoothly join those together with a curve. So starting at 0, 0, I'm going to go up and hit the first point, which is the crest. Then we're going to go back down and we're going to cross the axes at the next quarter wavelength. Then at 3/4, we are going to go down and pass through the trough. And then at the 4th quarter, or 1 full wavelength, we're back at the beginning. And we repeat that process again for the second wave. And I'm also trying my best to make sure that the wave, whenever it's hitting the crest or the trough, that it is curving a bit. So I'm not drawing triangles, I'm not just simply joining the dots here, but I'm actually smoothing those out so that we get that sine shape that we're expecting. So we've got 2 full wave cycles on here, but that's not enough for this question. We need to now add on information to this diagram that we've worked out and information from the question. So we are showing displacement against time. So displacement is here on the y-axis. And that displacement is measured in centimeters. So we'll do / centimeters. What we can tell from the question is that the amplitude of this wave is 4 centimeters. So I'm going to mark out where the crest of our wave is and put 4 on the axis here. That also means that the amplitude below the rest position is also 4. So I'm going to mark out that point and I'm going to label that as -4. Minus indicating that it's in the opposite direction. Now if we look at the x-axis, we're showing time here on the x-axis, and that time is measured in seconds. We calculated earlier that the time period of the wave was 0.2 seconds, which means the time for one full cycle is 0.2, which means that this point here on our graph is 0.2. That means that our second wavelength would be at 0.4. So now let's look at part B. We're now being asked to calculate the wavelength and then sketch a graph of displacement against distance to represent the wave, showing 2 complete cycles. So let's start off with working out what is the wavelength of the wave. So we know that we have our wave equation, V is equal to F lambda. We know the speed of the wave is 10 meters per second. We know that the frequency of the wave is 5 hertz. And then that's multiplied by lambda. So we have all the information there, we've put it into the equation, so now we just need to work out what lambda is. So lambda will be 10 divided by 5 to give us 2 meters. And that unit is meters because the velocity or the speed of the wave was given to us in meters per second. So the wavelength here is in meters. Okay, so now we want to sketch this onto a graph of displacement against distance. So we'll draw out the axes first of all, just like with the last question, and we'll put the wave, 2 full waves on that diagram, and then we'll have a look at putting on some key values to that graph. Okay, so on this graph then we have displacement against distance. So I'm going to put D here on the x-axis for distance and / meters. So we have 2 full wave cycles here. We know that the one wavelength is equal to 2 meters. So we can label on, put some numbers onto that x-axis, and at the end of one full wave we'll label that as 2. At the end of the second wave, that will then be 4. I can also put the amplitude onto the graph here. Looking at the displacement, our maximum amplitude is 4 centimeters, and it's -4 then below the x-axis. So finally we're being asked to calculate the phase difference between 2 points on the wire which are 0.8 meters apart and 2.8 meters apart, and our answer is to be given in degrees. So in order to calculate the phase difference, what we need to do is work out what is the fraction of the wavelength or of the period that separates these 2 points. We know that they are 0.8 meters apart, but we need to figure out what is that as a fraction of the whole wavelength. So what we do is we take our 0.8 meters and we're going to divide that by the wavelength, which we calculated earlier as 2 meters. So that works out to be 0.4 or 2/5. That's the fraction of an entire wavelength that we have. You can write this as a fraction as 2/5, or you can keep it as a decimal as 0.4. Either way, you're going to get the same answer. So 2/5 of a wavelength. Now what we want to do is convert that into degrees. So for one full cycle, we have 360 degrees. So one wavelength would represent 360 degrees. However, the separation that we have is only 2/5 of a wavelength. So 2/5 multiply that by 360 degrees, and that gives us an answer of 144 degrees. So that is the phase difference, 144 degrees. We first work out the separation, which in this question was already given to us. We then work that out as a fraction of the entire wavelength or period, if that's what's given to us. And then we multiply that fraction by 360 degrees. And that will give us the phase difference in degrees. Okay, part C of this question. We now have 2 points on the wave which are 2.8 meters apart. So we want to figure out the phase difference between these 2 points. So you'll notice that 2.8 meters is greater than the wavelength of this wave, because we know that the wavelength is 2 meters. So I'm just going to break this up in that we have 2 meters and then we also have an extra 0.8 meters on top of that. That's our 2.8 in total. So as we said, then the 2 meters here is one wavelength, which means if we have a wire and we have a number of waves on that wire, if we pick one point, I'm going to select a crest here. Well, 2 meters later from that crest, we're going to have another crest because that's what our wavelength is. The distance between one point on a wave and the same point on the next consecutive wave. So if they're both at the same position, well, that means they have a phase difference of 0 degrees. They're both in phase. So when the first point is at a crest, then the second point will be at a crest. When that first point is at a trough, then the second point will be at a trough. When it's in the neutral position, the second point will also be in that equilibrium position. So those 2 points are moving exactly in phase. So we can actually leave out that 2 meters. In fact, that would be true for any number of full wavelengths. So all we're really interested in here is this extra bit that's been added on, the 0.8 meters. Because there is no phase difference between any number of full wavelengths. So just the extra bit will give us the phase difference. So if we take that 0.8 meters and we divide that by the wavelength, which is 2, then we're going to get 2/5 or 0.4. I'm going to keep it in a decimal this time. In the previous part of the question, I kept it as a fraction. This time I'll keep it as a decimal. Both are absolutely fine to use. So our fraction then, the difference between the 2 points on the wave is 0.4. So what we'll do next is we'll take that 0.4 and we're going to multiply that by 360 degrees. And what we find there is we get a phase difference of 144 degrees. That's actually the same answer as the previous part of the question. So what we actually see here is that if we have a full wavelength in between, so we had 0.8 to begin with and then we had 2.8, we find that the phase difference is exactly the same. And that would be the same if we kept adding on a full wavelength. So 4.8 would have the same phase difference, 6.8, 8.8. They would all have the same phase difference. So when we're looking at phase difference, the answer will always be between 0 and 360. It will always be less than one full cycle.